Hey everybody, this is Mike Bartles from the Hydrologic Engineering Center. This video is a recording of a webinar which was made to the Federal Emergency Management Agency's Engineering and Mapping Community of Practice in October 2024. The presenters within this video include personnel from both the U.S. Army Corps of Engineers and the U.S. Geological Survey. From USACE, you'll hear from myself, Avital Breverman, Greg Karlovitz, and Chris Cook. From the USGS, you'll hear from Nancy Barth, Jim Lenoir, Scott Hamshaw, Sarah Murphy, and Robin Glass. Within this presentation, we provide an overview of an ongoing federal interagency work unit that is improving mixed populations analyses throughout the United States. Enjoy.
Thank you for the lead-in, Dave, on this one. And we're really excited on behalf of my colleagues from FEMA and the USGS and the Army Corps. We're really pumped up to show you what we've done over the last 2 years and kind of get people talking and get the conversation started. So today we're going to talk about flood frequency analysis and flood typing. This is an interagency collaboration approach to address with what Bulletin 17C couldn't get to or be mixed populations. Next slide.
My name is Mike Bartles. I am a hydraulic engineer at HEC. I'm part of this awesome team as well that's been working on this. Mixed populations have been a thorn in my side, pet rock, I don't know, depending upon the day of the week, for a very long time. So I'm extremely excited to be able to work on this with such an awesome team, but also be in front of everybody here talking about what's near and dear to my heart. So please hit us up with questions as we go too, and we'll do our best to get to them. But as a brief outline of this presentation, first I want to make the case for why you should care about this work. I don't want it to just be us yelling at you for an hour and a half. Let's first talk about why you should actually care about this, why this makes an impact to what we do as water resources engineers. I'm going to give a brief overview of the work unit, or we're all going to give a brief overview of the working unit, specifically talking about what we've done in previous years, and then a whole lot of what we've done this past year, which is really awesome, very, very cool stuff. And then bring it all back around to where we're going, what we're hoping to provide in the next few years as well. Bonus points if you know what dam that is and what year in particular. All right, next slide. All right, first let me talk about why we should care. Typical flood frequency analysis assumes that the data that you're using is IID. We throw that acronym around a whole lot. And by IID, I mean independent and identically distributed. So a typical flood frequency analysis is something like we're showing on the right-hand side, or typical outputs that you would see. Right, the black curve represents median estimates from the parameterized log Pearson 3 distribution. So you take those data points, those black circles, and you actually parameterize the log Pearson 3 distribution, so the mean, standard deviation, and skew. And then with that, you can actually make estimates of flood frequency quantiles and their uncertainty around that area. But obviously this one should stand out for you. Something ain't quite right with that one, right? Specifically the second part of that acronym, identically distributed, we're assuming that one parent population is creating the sample. So when we reach into the bag of possibilities and pull out floods from every single year, an annual maxima for every single year, those are coming from approximately the same parent population. In this case, that is not being guaranteed in this case. So how much trust do we have in the extrapolation? Working for the Corps of Engineers, we're always to the right-hand side of that curve, right? We're extrapolating beyond the range of observed data. We want to know what is the 1 in 100, 1 in 500, 1 in 1,000, 1 in a million annual exceedance probability discharge or volume. So in this case, that's not so good. Not a whole lot of faith in that one. Let me kick it over to Nancy for a bit more info.
Yeah, well, thank you for lead. I'm sorry, Chris, can you go back? I apologize. Thank you. So yes, unfortunately, this is one of the sites, long-term sites that we had to deal with after 35 years of not publishing flood frequency estimates in the state of California. So this is one of the sites that we highlighted when we were updating at-site flood frequency, regional regression equations for ungauged basins, and regional skew. This was in the mix, and we knew we had violated all the assumptions that Mike has talked about. And so typically in mixed populations, you see this S-shaped curve, this dog-leg curvature that really tells you that you have potentially different flood generating mechanisms that we should address and look at for extrapolation. Next slide.
All right. So if you've been around for a while, you've known that we've talked about this problem for a really long time. way back in the day, the grandfather of HEC, the person who actually kind of was um, the creator of HEC, Leo Beard, if you go way back in time, he was talking about this in the 50s and 60s, right? Specifically in the northeastern United States, and with regards to tropical storms and how they completely blow up the right-hand side of your flood frequency curve. If you were to fit that all as one single causal mechanism, your skew goes off the charts, and it's kind of wonky. So why are we talking about this for such a long time and not actually done anything about it and kicked the can down the road? In a nutshell, it's really hard to classify these flood types. Right, here's an excellent example from Nancy's paper where she actually did do that. Right, you go through the individual annual maxima and you say, this is of this type, I'm going to put it in this bin. This is another type, I'm going to put it in a different bin, and so on and so forth. That's hard to do, right? And we also have problems when we already subdivided a limited sample. Go back to the Northeast as well. So maybe we have 100 years of record, 100 years of annual maximum flow to fit an analytical distribution. That's awesome. Tons of data. What happens if your 3 largest flood events are from a tropical storm? Do we want to put that into a bin of just 3 and then try and infer what the likely 1 in 100 or 1 in 1,000 annual exceedance probability flow is? It's really hard to do that when you're already subdividing a limited sample. We don't have an infinitely long period of record with which to deal with, right? We're really missing guidance on how to do that. Even better, what if we just gave you that? What if we gave you the IID samples and told you what to do with them as well? Even better. All right, Nancy.
Yep. So thank you, Mike, for the lead in for that. That's perfect. So this was not an arduous task. This was one of 3 papers that I did for my PhD, going through the minutia of trying to figure out what likely generated these annual peak flows. And so this is another site in the Sierra Nevada that motivated my research. And you can see that the biggest, highest flows that are substantially bigger in flood magnitude and occur different in the cool season months at this high elevation site, these were actually deemed to be atmospheric river driven floods. So, but we also see those are the same flows that are deviating from the overall single population to the annual peaks. Next slide. So we came together, Mike Bartles, me and others. He said, hey, let's talk the state of science between our 2 agencies. What can we, champion together? We both know that the Corps and the USGS have to deal with sites like this. We have no statistics or we have no federal guidance on this. So we pitched it to FEMA, and David Rose and others thankfully funded us to work for 4 years together with some pretty lofty goals that the Corps and the USGS have not worked together on before. So these are a list of goals that we're slated to address, and this is to improve, why we came together, a mixed population flood frequency analysis methods. Then we're going to look at and talk about today the development and testing of semi-automated methods for determining flood type classifications. Then ideally, we're going to take that and we're going to develop a storage system for these flood type classification information that we can release to the public that they can use for these IID samples. And then we'll go one step further and to look at projected future floods of different recurrence intervals, considering potential changes in the proportion of floods originating from different combinations. And this could be motivated by changes in meteorological drivers and or antecedent watershed conditions, for example, with the end goal at the end of this 4 years that we want to have a prescriptive plan for national implementation of this upscaling of what we're going to talk about today on the flood and storm typing. And this includes training of federal employees. Next slide. But this takes a village, as Mike alluded to, and what I love to see is so many folks from FEMA, the Corps, and the USGS that have participated in some capacity in the last 2 years. And I know every single person would love to say, how much they've appreciated this inner collaboration between our agencies. But this is very unique compared to HFOG or APWE. This is us getting in there together, where the USGS and the Corps together are working on the current state of science to advance that. And it's not just siloed between agencies, it's really a bigger group working together. And you'll see in the future discussion in today's presentations, it's these little smaller vignette groups working together collectively for the big whole. So I kudos to everybody who's worked on this and contributed with it. And next slide, please.
All right, so we just finished year 2 of this effort. It's 4 years, as Nancy talked about earlier. We're right in the meat of it. We have some really cool things to show for it. We have a lot of stuff to look forward to in the future, but I'm going to talk about what we completed in previous years, so prior to this past year. Um, First off, we did a comprehensive literature review, as we should start. Let's see what others have done. As part of that, we identified a whole bunch of seminal papers that really talked about how to perform mixed population flood frequency analysis, or how they have been done in the past, in addition to how to uh, determine flood causal mechanisms, storm types, things like that, not just throughout the continental United States or United States as a whole, but internationally as well. Some really good work that's come out of Europe that's shown us a lot of interesting techniques that can be used to achieve these desired goals. We also came up with a whole bunch of different tasks or experiments that we wanted to investigate further. How do we come up with these individual flood causal mechanisms? How do we do this in an automated fashion? How do we fit analytical distributions or empirical distributions to this to infer flood frequency? Well, we wanted to test those in real world locations, so we just, selected a whole bunch of pilot regions to perform these actual statistics. We had a whole bunch of different ones that we went through various different selection criteria to come up with. They're all shown here, right? And out of that, we wanted to come up with calibration and validation regions. Right? You advance one for me, Chris. This is what we were left with. So we essentially grouped everything into three different meta regions. One is mountainous, one is central plains, and one is the humid east. We selected a region where we're going to develop these tools and techniques, and then another one where we're actually going to test them independently, right, without modification. And out of that, we came up with the Puget Sound, Upper Colorado River for the mountainous west, Red River the north, and Iowa River for the central plains, and Delaware River and the Trinity River for the humid east. We will come up with these estimates of come up with IID samples, tools and techniques for fitting analytical distributions, probability distributions, what have you, and test them within all these regions going forward. So we're going to use these over and over and over again as well. All right, next one. I'll kick it over.
All right, hi, I'm Jim Lenore. I'm a hydrologist with the USGS, and I'm going to be going over the data we're using in this project. Starting off looking at stream flow data at USGS gauges, we can access these data using the data retrieval package in R. And we're working with instantaneous flow values and daily averages. We're using daily averages to develop our time series. And that's an example of the plot there on the slide, showing an example for daily averages. And with these, sometimes the peak flows get muted by the averaging. And that's why we're using the instantaneous values also, is to get at those peak flows. Next slide. So now I'll get into looking at some of our land surface data and meteorologic data that we're using in this study. And when we're working with these, it's important to consider that these are historical data we're using to determine flood producing mechanisms over periods of interest in these pilot regions. And we're not using these data to simulate precipitation runoff processes in a model. And this helps us in kind of guiding how we're going to decide which data sets to use and working with the data. And then we also had some general criteria with selecting data sets. We're looking for data sets with a long period of record, high temporal resolution, CONUS-wide geographic extent for consistency across basins and for the upscaling of this project, and data sets with a fine spatial resolution so we can capture mechanisms in some of our smaller subbasins. And then there were some variable specific criteria that were considered on a case-by-case basis. So this table we see on the slide here, these are the land surface data that we're using in this study. The variables are listed across the top there. All of the data sources that were considered are listed below, and the ones that were selected are shown bolded and in green. And these selected data sources are also hyperlinked, so I believe these slides are going to be shared, so you can go in and look at these in a little more detail a little bit later. Next slide. So now we're looking at the meteorological data. This table is formatted a little bit differently. The variables are listed on the left. The data sources are listed in the headers going to the right, which are also hyperlinked. The data sources that were considered for each variable are shown with the black X, and the ones that were selected are bolded in green. Now, precipitation is not included in this table because there were many data sets that were considered, and we'll have a discussion on precipitation a little bit later. Next slide. So now I'll go into a little bit of looking at how we selected some of these data sources using temperature and snow water equivalent as examples. So expanding a little bit beyond those general criteria, starting with temperature on the left, we found that in literature reviews, many other flood typing studies were using degree day models. So we wanted to focus on that. And considering temporal resolution, a lot of the pre-1980 data only contained daily values, and finer resolution might not be needed for flood typing. So that's what we kept in mind when we're considering the temporal resolution. And on the plot, it's showing the data sources that we considered, and the length of the bar represents the period of record. We see a year across the x-axis at the bottom there. To the left of each of those bars shows the spatial resolution for each data source. And then red bars represent data sets with sub-daily values. Black bars have daily values. And for precipitation, we are working with the PRISM data set, LIBNA, AORC, which is NOAA's analysis of record for calibration, and 20CRV3, which is the 20th Century Reanalysis Project. And shifting over to the right, that's snow water equivalent. This is very important in regions that receive snowfall. And of the 6 data sets that we considered, 4 that we are working with are the ones shown in boxes there. The first one at the top, this UA data sets from the University of Arizona. This also includes snow depth. SNODAS, right below that, is the Snow Data Assimilation System from NOAA. And this also includes other variables such as snow depth. LIBNA below there, this was selected for its long period of record. And then finally at the bottom, that 20th Century Reanalysis was also selected for its long period of record and its high temporal resolution. Next slide.
Okay, so I will be going over some of the precipitation validation. My name is Sarah. I am a physical scientist with the New England Water Science Center. So this shows the precipitation data sets that we've looked at. Precipitation at various time scales is widely used in different flood typing studies, as it is the mechanism behind these high stream flow events. But also when accumulated over long periods of time, it can be indicative of antecedent moisture conditions, and it has implications for runoff and stream flow magnitudes. So it's really important we make sure that we trust our precipitation data sets. We compared over 24 gridded precipitation data sets for future flood typing, and they varied in spatial and temporal resolution, period of record, data quality, and the source of the data. And so in this figure, the colorful one on top, you can see the range of data sets that we looked at, and these are sized by the resolution, width by resolution and length by the period of record. We narrowed this huge list down using a literature review to a more manageable set that we've selected based on the resolution, period of record, and quality of performance. So basically the sweet spot between all of them, and those are highlighted in red. One thing to note, though, is that the 20th Century Reanalysis, which is the really thick one that's highlighted in red, while that does have a coarser resolution, it has that long period of record, and that's really critical going back to look at some of the peak flow events going back to the late 1800s. So that's why we selected that one, even though it doesn't necessarily have that high resolution that we were looking for. So to do the comparison, we took the grid cells closest to GHCN daily stations and compared annual and seasonal data and multi-day extreme precipitation to make sure that it was matching up. So the figure on the right is a Taylor diagram, which summarizes how well they matched up. You can see standard deviation is on the bottom axis and correlation is on that rounded axis. And then we have our centered RMSD, or the root mean squared difference, in that circle with the arrow. And so basically we want higher KGE values, which we can see below. That will be a better performance and closer to that, that highlighted circle there. So next slide. Overall, we decided that PRISM and LIBNA performed the best, but this wasn't surprising because they use station data within their development, so it makes sense that they would match up the best. The reanalysis data had relatively low skill capturing precipitation at the right time and place. And we do note that there could be undercatch of snowfall in some of these stations. So the reanalysis may actually be more correct than the gauge data, but we're not sure about this without further digging into that. On the right, we can see this time series. These are water year total precipitation and stream flow depth for some drainage basins. And these are drainage basins with low evaporative fraction. So the stream flow and precipitation should be directly correlated here without the evaporation. And we're seeing that there is some mismatch here. So we may need to look more into a water balance model to kind of tease out that kind of thing. But that is something that we're looking into in the future, as well as doing this same analysis with the snow water equivalent and the temperature data that Jim briefly went over just before this to make sure that we are not trusting any data that has any inaccuracies. Next slide. And I believe this is Scott.
Hi everyone, I'm Scott Hamshaw, machine learning specialist with USGS. The variety in data sources and coverage of the variables we just saw highlights, I think, the importance of setting up reproducible and scalable data pipelines to prepare model-ready data. And model-ready here refers to processes such as aggregation of variables to a common date-time index, consistent variable naming, missing data handling, those types of things. So here illustrating a workflow that we're using to take gridded data such as rainfall, soil moisture, and produce input files for each gauged basin, as well as extract the end day periods before and after a given flood peak date. So this allows us to readily scale our data processing to thousands of stream gauges and tens of thousands of flood peaks. We use a combination of tools to do this, including HEZ Vortex to compute spatial summary stats, and AWS S3 and SageMaker for running jobs in the cloud. So this workflow enables the team to perform the weather and flood typing that will be shown with the dashboard demonstration, and also enables future research tasks involving mixed population flood frequency analysis, cluster analysis, and potentially machine learning too. All right, next slide.
All right, hello everyone. I am Chris. I am with Army Corps of Engineers. I'm going to talk about the weather typing dashboard. So with this project, there's a whole lot of data. You have these multidimensional rasters for different parameters from different sources. You have those being fed into Vortex with shape files to produce time series data, these DSS files. And it kind of makes a conundrum when we're trying to view this data effectively and efficiently, especially in the case of trying to do manual flood typing and weather typing. So the main benefits of this dashboard are, one, are that it's interactive. Users can quickly parse through what I like to call unwieldy data. And the second is that it kind of provides a nice standardized baseline for people to do their manual flood typing and storm typing, because you don't have people working in their own little boxes. They're all viewing it in this dashboard. And I'm going to do a quick demo of what this dashboard looks like. Okay, so you'll notice here, so this is just running locally in my browser right now. You'll notice here we're on this guidebook tab with all this wonderful documentation that Sarah made about how to use the app, the data sources. And the reason this is here is because we're hoping to get this released in some capacity, possibly even public facing. But moving on to the functionality of the app, you'll see I have these overlay tabs and this gauge time series tab. The main idea of this is to combine, or to let a user holistically look at what's going on at an atmospheric level over all of CONUS in tandem with individual time series from these gauges, from the outputs of these Vortex, from the Vortex software. So you'll see here, there's a couple things going on. Select storm. These are all storms from the IB-Trax data set. It's a database of storm tracks from NOAA. You'll see I've selected Ivan, and this map here shows the storm path of Ivan in 2004. And then we also have cumulative precipitation. So this is the cumulative precipitation over the duration of a storm as defined by the IB tracks dataset. And some features I want to point out is Nancy thought it would be really nice to have, hey, let's have dynamic cumulative precipitation so a user can see possible effects of a storm after the official technical end of a storm, and to let a user interactively look at that. There's ways to view geopotential metrics, so geopotential height at the 500 millibar level on a given day during that date window. And there's also geopotential height anomalies, which is the heights normalized by long-term monthly mean. And there's also gradient, which is like a digital elevation model of those heights. And you can parse through and look at it over the date. And the idea of this, again, is to give an overview, synoptic look over what's happening atmospherically over CONUS. Overlay by date is another tab very similar. It just takes out the storm part, so a person isn't limited to just looking at storm dates and they can go through wherever. But the other tab I really want to point out is this gauge time series. Like I said, you want the app to be able to let users see different parameters affecting a gauge in conjunction with the more synoptic view. So you'll notice I have a DSS file path here. For context, I do want to show you what that kind of looks like. So this is the context of this is the contents of a DSS file. Every row in this DSS file is an individual time series. So these are all for the same gauge, just 0, 1, 4, 7, and so on, for different variables like mean sea level pressure, snow water equivalent temperature, all from different data sources. And that's what we're going to be reading into the app. So when I'm loading this file, what's happening is that gauge ID in the DSS file is being communicated with NWIS, that data retrieval package mentioned earlier. And now we're pulling down every annual peak flow date for that gauge ID. And I'm going to go to 2004, September 18th. And now down here is where you can select a window surrounding the annual peak flow date for which data you want to see. So I'm going to make those plots. So the daily flow data. All right, here we go. The daily flow data is also pulled down from NWIS. And then we also have all this other data, the convective available potential energy, the CAPE, the sea level pressure, temperature, snow water equivalent. That is all contained within the DSS file. And basically we take this date window and filter it by this date window. So now you have all this time series data for this gauge, which by the way is in Pennsylvania. And now the user can look at it in conjunction with what's going on over here, get a whole view of CONUS. I won't go into the interpretation, I'll leave that to experts, but I just want to go over the utility of the app. All right, I'm going to go back to the slides now. So a very coarse overview of kind of what's happening under the hood. For those overlay tabs, like I said, we have the IB Tracks storm path data set. And I'm going to highlight a few of the really nice R packages that made all this possible. SF for reading in spatial vector data. For those multidimensional rasters, they were netcdf files. There's a really slick R package called Terra. It's great for manipulating raster data in R. Honestly, it's kind of fun to use. And then you can have that, plot that with ggplot and R Shiny. Gauge time series, right? We have that DSS file, which is a format made by HUC, by USACE. But there's also an R package developed by some USACE personnel for reading in those DSS files into R. And now we also have data retrieval mentioned earlier. So we can take the gauge ID in the DSS file, communicate with NWIS, pull down peak flow dates, peak down daily flow values for those peak flow dates, and then make plots with everything in that DSS file. And the last thing I want to touch on is collaboration. So I, for one, find it really hard to share anything within my own organization, let alone across multiple agencies. So the current solution to this for using it internally, it's not the most elegant, but it seems to be working for now. It's that we have it as a standalone zip file, basically structured as an R project. And then so we have whoever wants to use it, they download the zip, they open the R project. RM is a package manager for R. All the correct versions of the packages will bootstrap itself to the R project when you open it. And then, yeah, hopefully it's worked okay so far. It doesn't account for things like operating system differences or version of R, but hopefully that'll all be moot soon because we're trying to put the app on a server. And this is what that file structure looks like. But that is what I have for you. I will turn it over to the next presenter.
Okay, thanks, Chris. Hi, everyone. My name is Avital Breverman. I work for the Hydrologic Engineering Center, part of the Army Corps. We're excited about the opportunity to talk to you about this work unit today. So thanks for including us. I've been working on mixed populations on and off for a few years, so this isn't my first rodeo. So I'll talk to you mostly about some of the tasks or the efforts that we completed this past fiscal year. So the first one was manual flood typing, and I'll tell you about why we actually decided to do that. As part of our literature review that Mike talked about, we came across a really nice review paper by Tarasova et al., a bunch of researchers out of Europe. And they looked at previously developed or existing classifications of floods. And they found that those existing classifications fall into one of three categories, either hydroclimatic, hydrologic, or hydrograph-based. And I'm showing you a table on the right from that paper. It's not an eye exam. I'm not trying to make anyone feel bad, but the size of that table is supposed to show you that there are many, many existing classifications that people have developed. They're not necessarily uniform, and one of the major drawbacks is that they've rarely been ground truthed or evaluated by comparing results with detailed information from well-observed events. So it's relatively easy to come up with a classification scheme if you don't actually evaluate how well it performs. So from this paper, we decided that flood classification frameworks should have the following characteristics. They should be robust, transferable, adaptive, and consistent. And I'll talk to you about how we've ensured that our classification schemes meet those four characteristics. Next slide, please. Okay, so when we first started this exercise of manually flood typing storms in our pilot regions, we sat down and we came up with what we hoped was a comprehensive list of flood causal mechanisms that affected the United States. So I'll walk you through this table starting from the leftmost column. We identified the primary mechanism, so this falls into one of three categories. The floods are either primarily driven from snowmelt, so snowpack is already on the ground. You have basically no input from liquid precipitation, and you just have rising temperatures that cause snowmelt or glacial melt. The next category, moving up this column, is rain on snow or rain and snow. So we have combinations of liquid precipitation falling on snow on the ground, or both liquid and snow precip falling at varying elevations. And then finally, probably the most interesting category is rainfall-only floods. So this is where we got to pull in some meteorology, and Greg will talk more about this. But if you've lived in the United States, which everyone does, you know that rain takes a variety of flavors, and this spans multiple spatial and temporal scales. And some of these types can cause more drastic flooding than others. So we've all seen tropical storms in the news very recently, unfortunately. And then there are smaller scale events like convective events. And so we wanted to be able to capture all of these types of primary mechanisms in our 6 pilot regions. So if you start looking to the right, you'll see that not every region experiences snowmelt floods, right? They don't affect the Delaware River Basin and definitely don't affect the Trinity. Some of these events like frontal rainfall affects almost every region. And so we wanted to span as many primary mechanisms as possible with our 6 pilot regions. To the extent possible, we also classified secondary flood causal mechanisms, so factors such as antecedent soil moisture, antecedent frozen ground, and wildfires. And secondary flood causal mechanisms are ones that don't cause floods by themselves, but can exacerbate or augment other drivers of floods. And this table was basically what we came up with to unify our classification. So initially, we were all using slightly different variations for causal mechanisms. So for instance, some people use thunderstorms, some people called it convective rainfall. Our ultimate goal when we upscale nationally is to be using consistent terminology so that there isn't confusion between analysts about whether a certain flood causal mechanism has different labels. Now I'm going to pass it off to Greg.
Cool. All right, next slide, please. I'm Greg Karlovitz. I work with the Hydrologic Engineering Center of the Corps of Engineers. I think I've been with this group a few times before, more in a context of some of the FFRD work. So you've probably heard me talk some meteorology before, and you can tell it gets me a little bit excited. So We're going to talk a little bit about the effort that we spent specifically on the subset of the flood typing effort that was focused on the meteorological aspects of this. There's a pretty intentional effort here to dovetail with our efforts on the FFRD front as well, because the capacity that we built here in the weather typing realm is going to help us advance the science as we continue changing how we're doing the hydrometeorology for FFRD. The question here that we really tried to answer was, can we find general atmospheric patterns or some kind of setup that's evident in a number of different data sources that help us tease out the meaningful differences between types of storms or types of floods that cause us heartburn when we're doing flood frequency analyses? And so, as Avital had mentioned, we identified a number of key atmospheric conditions that really start to cause differences in the response of the flood. It could be largely due to the spatial and temporal patterns and extents of the rainfall. It can be the seasonality and its interaction with antecedent conditions that cause these sorts of things. But we tried to make the most meaningful distinction by looking at these large, broad themes without getting into really way too much detail. And what we really found is that throughout the country, we could classify it into largely like mid-latitude cyclones or extratropical cyclones were kind of the key meteorological theme for a lot of these, especially these cool season storms. Atmospheric rivers, which can happen in surprisingly more areas in the United States than you typically expect. Most people are familiar with Pineapple Expresses on the West Coast, but we've seen signatures of atmospheric rivers throughout the country. We see fronts, big bubbles of temperature differentials of air that cause rain events. We see convective storms, so some of those really violent, intense thunderstorms throughout the country. And then obviously tropical storms tend to be the ones that cause the biggest departure in our flood frequency analysis. So we were developing the tools to identify those. Next slide, please. And our weather typing approaches, really there was a spectrum of approaches that we applied here. And part of this was built on our capabilities with local expertise. Realistically, neither the USGS nor the Corps really have a huge cadre of meteorologists available, but we tried to engage with the ones that we do have to try to bring the expertise to the larger team. And so we employed a kind of spectrum of strategies when doing the meteorological classifications that incorporated both an interpretation of data and an interpretation of maps. And so we'll show a couple of examples in a couple of slides here of interpretation of maps. But the real goal here is that we need to build robust training data sets to be able to use automatic classification later on. And so what that meant was we have to squeeze as much information out of the data or the maps or whatever information and expertise we have. And so we explored a whole variety of different ways of interpreting this historical meteorological data to make these classifications. The hardest part about this is weather is complex. These storm patterns are complex. They have their own nuances and differences, and it takes a little bit of expertise in order to make these things happen. Next slide, please. So what we did is we formed a little task force, kind of a focused group of people with interest in working on meteorology. And it turns out that hydrologists and hydraulic engineers tend to have a lot of interest in meteorology. So we had no shortage of people who got involved in this. And what we did is we established regular meetings with open discussions and a sharing of results and findings, and most importantly, requests for help. And what this encompassed were the efforts everybody was doing in their own watersheds as they were going through the weather classification to share what they're seeing, share what they're thinking. We worked through things, for example, the map on here, this is an invaluable tool. This is a 500 millibar height contour map from the daily weather maps. And one of the topics that we were talking about is how do you interpret a map like that? How do you interpret surface analyses? Things like that in order to build up the capacity internally for us to make good classifications, build good training data sets, but also in general to improve everybody's skills to make them better at doing these things. We had to connect our experts with our learners and get everybody up to speed on doing this in order to put out a good product. Next slide, please. So what analyst-driven weather typing really looked like was poring over the really long period of record of daily weather maps. What's beautiful about these is they go back to the mid-19th century, and they're fairly consistent in terms of what they indicate. As time goes on, they get more sophisticated and they include more data. But what they give you is an eagle-eye view across the country of what was going on in the weather. And these synoptics are crucial for identifying the meteorological cause. The beauty of using this approach is that it's consistent with respect to time. We're looking at roughly the same information going back a very long period, and an analyst is making sense of it. People are very good at finding patterns. So things like what we're seeing on the daily weather maps here, the lower right is showing a mid-latitude cyclone parked somewhere over Minnesota and Wisconsin. And that's really clear to anybody who's seen a lot of these maps. That's a mid-latitude cyclone. And you're going to see that pattern pop up time and time and time again. It's very hard to summarize what's happening in that map in a single statistic or number. So sometimes the expert eye looking at these things is extremely valuable for making these classifications. There's other aspects of this as well. For small scale features, things like thunderstorms, in the upper right here, we see the hatched area is indicating where rainfall is occurring on the surface map. And inside the little red boxes is that familiar little symbol for thunderstorm bearing rain. And so the trained eye, again, goes looking for those things as an explanation for why it was raining. Now, there is an inherent subjectivity to this process, especially when some of these surface maps get complex, or it was a smaller magnitude flood, and so the amount of rainfall might have been less. And so it starts to break down a little bit where two different analysts might get different results, and that's where bringing in the data really becomes the valuable part of this process. Next slide, please. So in terms of the data, we built this weather dashboard collaboratively in order to give people all the information that they needed. And really what it came down to is cobbling together the best available data for the period of record. So for some of these USGS gauges, the record goes back really far, and it goes before some of these data sets even produce any data. Livna starts in like 1915, and we had flood peaks that were happening into the end of the 19th century. And so what we had to do is come up with ways to make estimates for those events early on. So we cobbled together those best data. And really what we try to do is we try to identify for some of these key variables, if they go above a certain amount or below a certain amount, does that tend to be more associated with one type of storm than another? Convective available potential energy is a great example. It's essentially a measure of the buoyancy of the air in the atmosphere and how much capability it has to lift a parcel of air high into the atmosphere. And this is typically a measure of thunderstorm potential. And so we used this as a time series of data that could potentially, when in conjunction with rainfall, identify convective events. And so you might look at that and say, okay, what's a value that might trigger that decision? And we start to hone in on a value of about 1 kilojoule per kilogram being a typical number that indicates vigorous thunderstorm activity. As you go through these events, you start to get more and more expertise on what these threshold values can be, and that starts to help you build the foundations of what might be an automated classifier later on. But a lot of us started to develop kind of flow charts and workflows that helped us work through the various data sets this is in theory more objective and repeatable, but it really does require expertise to build that framework in the first place. Now, one of the concerns with doing something like this is if we start to implement automated processes, if the automated process and the independent check on that process are built on the exact same data, then it's not really an independent check on one another. And so that's one of the potential downsides of driving this purely by data and not having sort of a secondary check based on like the daily weather maps. But in some cases, in order to be able to actually make these classifications, it's the only way we can do it. Next slide, please. And so really what it all came down to is it's like all of these things, it's the middle ground on all of these. We have to find the strengths of both approaches. We use the daily weather maps, and thanks to their long record and consistency, that gave us an anchor to really have some confidence in some of these classifications. But then, finding out what the eye saw and comparing it to the time series data allowed us to bake in a certain amount of objectivity. And so when we went through and classified these events, a lot of us went back once we started establishing thresholds for data values like CAPE or precipitation, and started to look then more critically at the ones that we manually classified using something like a daily weather map and start to refine those just to try to find that middle ground between our very capable pattern matching brains and what the data were indicating. And so realistically, what this turns out is a training data set that's as close to the so-called truth as possible so that we can start with a process to build automated classifiers and test them in a way that gives us some hope to be able to scale this up across the country. Next slide, and I believe I am handing it back to Avital.
Yep, thanks, Greg. All right, so Chris talked about the weather typing dashboard. Greg talked about our weather typing task force. So all of those were used in an effort to actually complete our manual flood typing process. So I'll talk about how we did that. We talked about our 6 pilot regions. And we basically elected a pilot region champion, so 1 to 2 people for each of those regions who were responsible for manually classifying every annual peak flow at 3 key gauges. And those key or representative gauges were selected to represent a range of record lengths, degrees of regulation, and land use changes. So we're trying to really acknowledge that these gauges are affected by varying degrees of regulation. There's been changes to the upstream drainage areas in terms of urbanization and land use change. And not all gauges go back to the 1850s, right? So we're trying to encompass all of those factors in our manual flood typing effort. We use basically a weight of evidence approach in this task. We already talked about how we used daily weather maps. So that's shown on the bottom right here. And that was a really great opportunity for a bunch of us to learn how to actually interpret those maps, interpret synoptic organization. We used the weather typing dashboard like Chris talked about. So that allowed us to visualize discrete storm tracks, precipitation accumulations, and then time series data extracted from gridded data. And then also geopotential heights, gradients, and anomalies. So that was really invaluable in our weather taping efforts. We were fortunate that we had quite a few previous flood and storm typing efforts or mixed population flood frequency analyses in these basins. Some of them were selected for that reason. And those previous efforts were done by the Corps, USGS, other entities. And so we leveraged those to compare our classifications to previously developed classifications. We also used post-flood reports. So I'm showing one in the top right here from Hurricane Agnes, and then monthly storm publications. So these are produced by NOAA, I believe dating back to something like 1959. And they give you mostly qualitative description of storm occurrences by state, but they're nice to kind of as a secondary check against other data. And just to note, so we picked 3 gauges in each region, and we decided that if multiple gauges were affected by the same event, that we would allow a different classification at 2 different gauges, right? So you might have the same event in 2002 that affected 2 of your 3 key gauges, but maybe you classified one as snowmelt and one as rain on snow, because that's what this weight of evidence showed you. And this acknowledges that there's spatial variability within these pilot regions and in our hydrologic and meteorologic indices, right? And this most typically occurs when you have large differences in elevation in your basin, as we did in a few of our regions. Next slide, please. Okay, so this is a 1-slide summary of one of our subtasks this past year. So it won't do it justice, but I'll do my best to summarize. The goal of manual flood typing was to inform automated or semi-automated flood typing. It would be great if we could manually classify every single peak flow at every single gauge, or by great probably sounds really overwhelming because we just don't have the capacity to do that, and it's not really feasible. And so the whole point of developing or going through the manual flood typing exercise was to inform classification algorithms that we could then use to upscale this effort nationally. So this was one of the tasks, like I said, was producing automated flood typing procedures. So we developed a procedure for our 3 calibration regions and then applied those classification algorithms to the 3 validation regions. Now we acknowledge that there's there's differences between our calibration and validation regions. So like I talked about a few slides ago, the Delaware River gets snow. To some extent, they get rain on snow events, but the Trinity River, which is the corresponding validation region, does not get snow, right? So we didn't have to worry about classifying rain on snow in the Trinity, but we did have other storm types that did not affect the Delaware River. So basically, there's overlap between our calibration and validation regions, but there isn't complete overlap. So I'll talk about the slide left to right. A lot of us use kind of threshold-based or flowchart-based approaches to automated classification. The one I'm showing on the left here is the Delaware River Basin located in the mid-Atlantic. So our first step was discriminating between only rainfall events and then some combination of rain on snow. And so we came up with a SWE depletion threshold. And that antecedent period varied based on the gauge's contributing drainage area, basically the time it would take for snowmelt to travel to our gauge. Our next step was to discriminate between tropical cyclone events and every other type of rainfall. The Delaware River has experienced basically some of its largest flood events from tropical cyclones, and so we felt it was important to separate those out. And we used a distance-based as well as a temporal window-based threshold approach to separate tropical cyclone events from other types of rainfall. All right, next I'll talk about what this basically showed us, because I think these results are really cool. So on the top right here, I'm showing the monthly distribution of flood counts at one of the key gauges in the Delaware River. This happens to be Beaver Kill at Cooks Falls. It's up in the headwaters of the Delaware. Our three flood types are rain on snow in red, rainfall in blue, and tropical cyclone in green. What I like about this plot is that if you have ever lived in the mid-Atlantic, you know that it can there can be floods and rain any time of year, and that's what this plot shows. So we have our rain on snow typically between November and April, with it occurring most frequently in March and April. There's quite a few flood events in those 2 months alone. Tropical cyclones are the least frequent, but unfortunately the most devastating floods that affect this region, and they typically occur in the June to October timeframe. And then rainfall is shown in blue, and hopefully you're seeing from this plot that it can occur any time of year. Although I will say that rainfall is most frequent from this plot in the late fall and early winter, and that's because most of these rainfall events are mid-latitude cyclones. And so we didn't discriminate all rainfall type of events if we didn't think that they were distinct enough from a flood frequency perspective. All right, on the bottom right here is how we assess the performance of our classification algorithms. And we did that using confusion matrices. So I'll talk about them because they are a bit confusing. This is basically a matrix. So on the left, on the y-axis, we have our manual classification results, and on the x-axis, our automated classification results. So on the dark blue diagonal, starting from the lower left to the upper right, those are the counts of floods that we correctly classified. So basically there was agreement between the manual and automated classification. So hopefully you're seeing that the vast majority of our flood events were correctly classified. If you read from the middle row from the y-axis, so rain on snow, and then you read from the x-axis going up, you see that we had 58 events that we called rain on snow during our manual classification that we also called rain on snow during our automated classification. So that's good news. We had 2 events misclassified at this gauge. You can see that in the lower right-hand cell. So basically what this says is that there were 2 events that we manually classified as rainfall, but the automated classification procedure called them tropical cyclone events. So not perfect. But the table on the right here shows very good calibration metrics, and these all assess slightly different aspects. So some assess how well the algorithm correctly predicted true positives, and there's slight variation in these metrics, but overall our algorithms are producing good results and matching our manual classification very well. Okay, I am now going to pass it on to, I think, Robin.
Hi, everyone. Hopefully you can hear me okay. Robin Gloss, USGS. I'm at the New York Water Science Center. And I'm going to introduce our task 4C. So this task is in charge of kind of coming up with the flood frequency methods, right? So now we've got our flood typing, we've got our peak flows, we've got our distributions. What do we do with those? How can we actually come up with the quantiles of interest? And so in the orange box in the middle, where is our overall goal of coming up with more accurate flood frequency estimates given the flood types attributed to each peak. So kind of we're attacking this from many different directions, and these methods are all under development right now, kind of in their infancy, and we're starting to apply those to some synthetic data sets so that we can directly compare them. So in the bottom left, we've got our baseline, which is to just ignore the different flood types and kind of business as usual fit everything to a univariate distribution. And then on the left here, we've got the classic kind of probability of union where you can just arithmetically combine the probabilities of the different flood generating mechanisms to come up with a mixed distribution. We're experimenting with peaks over threshold sampling, which instead of taking the annual maximum every year, we would threshold the time series. This would need to be done with the daily average time series essentially, because you would look at more than one. You wouldn't just look at the highest peak per year, but you might look at the second highest peak, maybe the third highest peak as well, and you would fit those to a different kind of distribution. And we're going to kind of compare that to a known estimate of flood frequency. And then over on the right, we have kind of more novel approaches that we're taking. So we have a postdoc on the project who is concentrating on Bayesian techniques that I'll talk about in just a minute to kind of get at either an informed or naive idea of what these different flood generating statistical populations might be and their associated parameters. We are taking a multivariate approach, and that's kind of my pathway, which I'll also talk about in a minute. And then we have the generalized additive models for location, scale, and space. And that is taking a weighted mixed populations approach. And Nancy Barth is heading that up. Next slide, please. So the Bayesian techniques, these are several different methods that are being developed. And so these include things like polynomial curve fitting, additive mixed models, Markov chain Monte Carlos, marginal moments, and single population models. And so our postdoc is taking all of these different techniques and he's looking at it blind, first of all. So without any knowledge of any flood types that are happening whatsoever, and just looking at the data, and can we kind of back out what the shapes of those distributions might be that are underlying that mixture. The multivariate approach is going to be using copula theory. So that's kind of my lane. The figure in the middle here is it's a pretty simple copula where we're looking on the y-axis of the probability of precipitation, and then on the x-axis, the probability of stream flow. And you can see that the two are loosely correlated to each other, and they might be correlated up in the tails, more in the middle of the distribution. And we can kind of harness that correlation structure. And the beauty of copulas is that it's a multi-dimensional correlation structure. So it's not just a single correlation coefficient, a single number. Instead, it's a two-dimensional shape. And we can use these bivariate copulas to harness the most likely return period value. So we can actually come up with flood estimates given the relationship between precipitation and stream flow. So the key to using a multivariate approach is that you need non-independent variables, right? So we've been looking at, probability of union and weighted mixed populations, where you say, okay, we've got the atmospheric river generated floods and the non-atmospheric river generated floods, and those are two independent populations. But instead, with a multivariate approach, we have to start thinking about linked variables and correlated variables. So I might be dipping into the data that was used for the flood typing, things like soil moisture, snow water equivalent, and how that might be correlated to temperature. We can upscale this to more than two variables. So what you're looking at here is a bivariate copula. And what we can do is we can link many bivariate copulas together to get the probability of, say, 3 things happening at once, 4 things happening at once, using something called a vine. So that's in development currently. And then over on the right is this, the gamless approach, which is extremely powerful. And I'm really tempted to combine it with the copulas to be able to model the marginals, because what gamless can do is it can really harness non-stationarity, and it can use external covariates like precipitation, like temperature, to say, okay, this is why the distribution is changing over time. And instead of just using time as a covariate, you can actually use physical variables to explain those changes over time. And you can improve your flood frequency estimates in non-stationarity. And then what she's additionally doing is she's estimating the ratio of the estimate of the ratio between the different flood types. So you're expecting maybe 30% rain on snow and 70% rain only, then you can use that to come up with an updated exceedance probability. I'll hand it off to Mike.
All right. First, we talked about how we came up with these better IID samples, right? We're planning on giving them to everybody, right? You got them. So which one do you use? Now all these different flood frequency analysis techniques that Robin just talked about, it's awesome, right? That's a great summary. Which one do we recommend using, when and where, right? Well, we kind of need an experiment that uses an even playing field for all these different techniques. And we also need one, unfortunately, that like gives us the truth so that we can compare against known values, right? If you're like me, I shy away from like really heavy math, and I use Monte Carlo equate frequency to brute force things that I can't figure out with a pen and paper, right? There's really, really good foundational papers that have been done that actually proved that these techniques are applicable. Most notably, Chowdhury and Stedinger from '91 that has been used time and time again. It was also used to justify 17C, adopting that over 17B and other techniques as well. We can use those same types of analyses to try and inform which one is best for use, and also where and how and why as well. So go to the next slide for me. All right, what we do is we start with truth, right? We're not looking at the Delaware River at Trenton, right? We're looking at a location where I know to a T, this is what the flood frequency distributions are. This is, just call it Mike's gauge. I know exactly what everything is, right? If I assume that that's truth, I can then reach into those individual bags, those parent populations, and pull out samples accordingly. So go to the next slide for me, or the next animation. That's what we get here, right? I've dipped into that for the 3 different causal mechanisms I'm going to say is at play at the specific location. And I've generated samples from those known distributions. Now that I have those samples, I can do a whole lot of stuff with that. I can use Robin's technique. I can use copulus to try and infer flood frequency. On top of that, I can use the baseline where it's just like, I don't know, just take the annual max out of all of those, which is what we do very often, right? The baseline approach. We can do all sorts of different things with these samples. But the cool thing is, if I take it the next step, once I fit all those distributions, the flood frequency analyses, you hit the next animation for me, Chris. Now I can compare against truth, right? I can start to determine how close was I? How well did this specific technique work against known data? Because I knew the truth to start with, I inferred sampling error by reaching into that bag and generating those individual samples, those IID samples. And then I fit distributions to them and came up with my estimate of flood frequency. Now I can compare against the truth to compute how accurate was I. And one more step, I can generate cool plots like this, right? Where I come up with bars of information, the mean square error or bias. You click the next animation for me, Chris. And you can look at specific quantiles of interest, right? We commonly are looking at the 1 in 100 annual exceedance probability. Maybe it's the 1 in 1,000. We can get all this stuff, right? Mean square error, bias, variance. How often are our confidence intervals truly encapsulating the true likelihood of flood frequency at a specific quantile or a specific AEP of interest? We can look at all sorts of different things like that to generate plots like this to inform our estimates or our model recommendations, right? So to say, our guidance on this is the right technique to use in this specific instance. We have a whole bunch of different test combinations that we're coming up with, different combinations of known truths, sample size. Sometimes this really, really matters, or a specific technique is much better than another one when the sample sizes are really small. Sometimes it doesn't matter that much when the sample size is really big. Sometimes it really matters when there's only 2 different causal mechanisms. Sometimes another sample or another technique works really, really well when there's 3 or 4 different causal mechanisms. These are all those test combinations that we have on the x-axis here. And the height of the bar essentially tells you how wrong the individual methods were. These are just made up. These are not for like public consumption. They're just made up examples right now. But this is what we're hoping to get out of this this step here, this task 4C. All right, go to the next slide for me, Chris. All right, now let me talk about the future, right? We talked about a whole bunch of stuff that we've already done. Where are we going with this, right? Now we want to plan on scaling this up, right? Imagine with me for a second that when you look at a peak flow frequency or a peak flow file, right, you don't just get the date, the stage, and the flow that's associated with that. Imagine you would also get what is the causal mechanism, right? Is this a rain flood? Is this a rain on snow? Is it a tropical cyclone? What type of storm event generated this? Was it a mid-latitude cyclone, or was there something else going on with that? We want to give you all of that information, and we also want to let you make an informed decision on what to do with that type of analysis, right? So we need to generate a lot of guidance, a lot of data, and a lot of examples for you to follow. And we also want to scale this up in the future, right? We chose these individual pilot regions because they include a whole bunch of intricacies that we want to make sure that we adequately represent, and they're near and dear to our hearts, right? But we want to generate a way to actually scale this up for the rest of the country, right? If it's in a homogeneous region, why couldn't that automated algorithm that Avatar was talking about be applied elsewhere? Why wouldn't the automated algorithm that was developed for the Delaware River not apply to the Susquehanna River? It should, right? We should be able to do that. So let's establish the scope of work for where do you get this data from? How do you manipulate it in a certain formative way? How do you apply this causal mechanism or this classification algorithm to it? And then also, what do you do with that once you actually get the IID samples that come out of this? So we have a lot planned for this. This won't just be something that you put on the shelf and never look at again. We hope that you use all of this information to do a better job of estimating flood frequency, because we do that all the time for justifying projects and actions, and ways that we operate our projects, right? We also plan to blow you away with tons of tech transfer and training materials, right? All of our prospect courses at HEC, we want to update. I know the USGS has similar plans as well for a lot of their training materials as well. We want to pepper you with tons of information that makes use of this new data. This is what we have planned for in the future years, in addition to some really other interesting stuff looking at changes over time as well. All right, I believe with that, we have hit the end. We still have a couple minutes left for questions. So if you do have any, please feel free to come off mute, ask us. I want to open it up for the other presenters as well, if they have anything to add. Thank you all for sticking around this long too. I appreciate that.
Thank you all. Yeah, that was great. As maybe some people digest what they just heard and were blinded by science, I'll ask, in general, what's like the overall result of shifting to a mixed populations approach versus a LP3 that assumes homogeneous causal mechanisms? Is it always that like that end tail gets shifted up to I guess like higher peaks or higher recurrence intervals, or is it variable about like kind of what the directional change would be?
It can be definitely variable. The ones from an agency perspective within the Corps of Engineers, the ones that we're really worried about the most is where we're coming up with false negatives. There's no problem here. We should just move on, and no big deal when it turns out that there actually is an actionable thing that we should do to reduce risk, right? So we're really interested in the ones that we're underestimating badly, so we can minimize risks for folks, right? But there are other uses to this data as well. I'm interested in the right-hand tail. I want to go out to rare exceedance probabilities, but that doesn't mean that these tools and techniques don't have their applications for more commonly occurring floods or low flows or things like that. So all of the things, all the tools and techniques, especially the semi-automated algorithms that we come up with, there's no reason that they wouldn't work for every single time step that's available, right? As long as the data is available, it doesn't have to just be the annual max that we're trying to classify. You can classify what you would like to classify. I'll let the USGS answer that one.
The comment section. Yeah, so there's a comment Mark asked. Yeah, will USGS increase the number of stream gauges? When and how many? Iowa uses acoustic water level gauges. Is that a good idea? I think this also gets to like the question about, you're only as good as the data that you have observed. And so I don't know how much USGS can speak to whether or not you're increasing stream gauges, but also maybe broadly speaking about, data availability at large.
So I can take a stab at this, and I encourage my other USGS folks to chime in. Maybe Robin, who works more directly with her respective cooperators for New York. But I can tell you in talking with some folks who may be familiar with stream stats, USGS stream stats, and the updating of that, led by Pete McCarthy and others as our stream stats coordinator. That's one thing that what Pete was really interested about just the inception of this particular program is, we know that we're data limited in some places. How can we leverage what's coming out of this study to not make it static, to make this available to the hydrographers in the next year when they're actually working the records, to come up with some attribution for the current year. Right. So ideally, the USGS would be, amicable to incorporating, and there's already a regional initiative right now being funded by Region 8 that we're looking at updates of peak flow files to accommodate this. From the perspective of does this lead to, additional stream gauging? I wouldn't know at this point, pretty early on.
I can speak from a Water Science Center perspective, and a lot of this has to do with the funding structure of the United States Geological Survey, where the vast majority of our stream gauges belong to or are stewarded by our water science centers, which are largely state funded. And so you see a lot of difference state by state because of the funding structures. I can speak to New York. We're adding a ton of new gauges. The governor just signed funding bill to, we're calling it our hydronet. So New York is adding a ton of new gauges, and we're also starting to implement digital imagery video to be able to tease out stream discharge. But that's New York, right? So it's going to be a little patchy across the basin.
Thank you all. Ted has a question. Ted, do you want to just come off mute and ask?
Sure. Yeah, I was just curious, anyway, really interesting topics. But one of the things I've noticed in our region is there'll be things like there might be one thunderstorm that just kind of totally breaks the frequency curve in a particular area, and then there won't be that kind of thunderstorm in any of the nearby gauges, but it could happen. And so it's trying to extrapolate these rare things that can happen more on a regional scale. Is there a thought to how that would get incorporated?
I can speak to it. I'll definitely open it up to other speakers as well. Yes, 100%. That is more easily discernible when you have more information, like the stuff that we're talking about providing in future updates. You can also, another really cool aspect that we're looking at in these next years is how has that changed over time as well, or how do we expect that to change in the future? I'm sure you're aware of concerns related to changing flood mechanisms. In the West, we're really interested in timing of snowmelt flooding, right? Is that going to shift sooner in time? And we're going to have to change our water management plans as well to better capture some of that information. So we are very, very interested in not just regional perspective, but how these things are also changing in time and what can we do to better anticipate and plan for that in the future as well. But does anybody else have something they'd like to add to that one? Hopefully I didn't shut anybody down. Good question.
No, I was going to mention really quick, this does have a little bit of the dovetail with what we're doing in FFRD, a little bit on the hydrometeorology front, and it wouldn't be a discussion with me if I didn't talk about stochastic storm transposition, but it's another way. So a lot of these approaches, what we're working on right now on a regional basis, really the goal is to engage in space for time substitution to the best of the extent that we can, right? So that there's no substitute for data. And when you don't have data at your site, you really hope that you have a regional signal or signals at other sites that will give you information about what you're looking at, which is part of the reason that we're, looking over some of these large test watersheds for information. And if we do get the weird ones, you identified, a potential one-off storm that occurred at one location, then if that's not present in the other ones or in the training data set, then it's going to stick out like a sore thumb. And that's the kind of thing that we're going to have to loop back to. But that's also some of the strength of what we're working on the FFRD front as well, as we're building up big catalogs of events that aren't so much tied to having to necessarily affect your specific location as it does affect something within your region. that we can then explore the impact to. So these two efforts are very complementary in that kind of way, where we're trying to exhaust sort of the list of potential mechanisms, but leverage all the different ways that we can look at, regionally speaking, how these flood mechanisms occur and attribute them as appropriate. So yeah, there's a lot going on that.
Yeah, this is Ben Pope with Compass PTS. I have maybe two sort of related questions. As we're sort of continually advancing the flood frequency methodology, it becomes sort of more complex. And I think the presentation here is very, very interesting, and I think very impactful, and looks like headed toward a significant improvement in the reliability of our estimates. But like I said, it's also more complex. So you talked a little bit about outreach and training as a future direction. Is that going to be directed toward consultants and contractors as well as the other federal agencies, practitioners? And then I guess the second part of the question is, so, coming from somebody that's done this for a while, the traditional approach for mixed populations, if you're certain about partitioning the record, then you partition the record, do frequency analysis on both partitions, and then do like a combined probability analysis. How does that, and obviously the problem with that is accurately partitioning the record, because it's more of a continuum kind of thing. At least where I'm at in North Carolina, hurricanes, well, just separate all the hurricanes. Well, is it a hurricane? Is it a tropical storm? Is it a tropical depression that almost made it to a tropical storm? Is it a nor'easter that comes down this way every once in a while? So yeah, I mean, it's obviously a problem, but I guess just, I don't know if you can comment on, if someone would comment on that.
Okay, do you want me to go first, Greg? I see you're unmuted. Okay. Personally at HEC, we make all of our training materials public for everybody, and we do open up our classes to non-federal and non-USACE personnel as well. Unfortunately, USACE gets first dibs on that, but all of our training, anything we would develop as part of this is publicly accessible. And I would imagine that we would spend a significant amount of time. We're all going to AGU this year. We'll have a ton of poster presentations and stuff like that, as well, that details a lot of these efforts. In future years, this next year, the year after, I'm sure we're going to be making the rounds again, putting on seminars, doing presentations, classes that detail these new tools and techniques as well. We will try and saturate the environment as much as possible to get the word out about this data. We want it to be used. We want these tools and techniques to be used as much as possible to improve everybody. Flood frequency estimates everywhere.
Great.
Yeah, I think one of the future keys to this too that you're kind of hitting on, Ted, is it's really how is this going to impact the federal guidance potentially in the future, and what are we as federal agencies going to do and recommend as we learn more about how to do these things? Because whatever the next iteration of federal guidance is going to be, hopefully it's not the same amount of time that passed between Bulletin 17B and 17C. It's good. We're going to have to contend with the fact that now there's a lot of people who are going to depend on implementing this federal guidance and are going to need data, tools, and training in order to successfully deliver that stuff. And so that's going to be the mission largely of the federal agencies who are developing and implementing then this federal guidance. So we're not going to leave you hanging. That's the promise. It's got to be multiple things though in order to make it successful. And really the goals of this work unit are to work out the hard parts of that now and get this stuff as squared away as possible to make actionable recommendations, things that people in the field can do to get their studies done.
Yeah,
that was Ben, not Ted. I'm sorry.
Okay.
Right.
Thank
To
you.
hit at the other part of your question, that what you described there is probability of union in a nutshell, where you fit separately, combine back together, fitting across the x-axis. That is the workhorse, as detailed in like EM 1415 within the Corps of Engineers. But we have all those novel techniques that are coming on. We don't know if the stuff that Robin talked about are going to blow the socks off of that. And if they do, we should be using those instead, right? So we're trying to test all of those things, and also make an informed decision for you, or at least make an informed recommendation of when and where those would be applicable, or fall flat on their face.
Yeah, I think a lot of what you talked about, first part of the presentation, sort of simplifies, well, it gets to the storm typing, which to me is the big hindrance now to trying to partition your data. I mean, maybe, out west, if you have snow melt and snow melt and then rainfall runoff, yeah, maybe you can partition that, but then you've got rain on snow, which sort of complicates the problem. So maybe you have 3 different types, but yeah, I think that storm typing stuff is pretty exciting and very interesting. So yeah.
Agreed. Thank you for your enthusiasm. I appreciate it.
So I got a message that there's a few questions that were asked, but I don't see them in the chat. I think they're from Christine Masula. Christine, do you want to just come off mute and ask the questions? Because it doesn't seem like they're coming up in like the broader chat.
Okay. I have quite a few. I guess
3 minutes left.
Yeah, okay, let me choose one. Are there any plans to involve NOAA in future interagency efforts?
Yeah, David, I don't know if you want to jump on that, but that's been a work in progress. We've been engaging with NOAA kind of on both fronts on the FFRD efforts, and they have, expressed some interest, at least in participating in some of the storm typing discussions for sure. So more to come on that. Nothing formal yet.
Nothing formal, but we have monthly meetings with folks like Kelly Mahoney and Sandra Pavlovic, and they're very interested in what we're doing, and we're actively looking for ways to collaborate.
And then maybe I'll ask one more. Does this storm typing exercise make flood frequency analysis for like the future easier, and how would methods need to be adjusted to account for future climate projections?
Okay, I can go again. So imagine those semi-automated algorithms that we already defined. What if we just provide a future data to it as well, future projections of climate, right? We can do the exact same partitioning of our expected flood peaks into the different bins going in the future. And we can also look at how does that change. Obviously, that's based upon the data that we give it, right? And the assumption that those different steps in the process along the way, if we're greater than this, we're of this type. If we're greater than that, it's of this type. Those things are static as well. But yes, we can do that. We can also look at historical periods as well to see how things have changed. But we also have a degree of uncertainty in the future as well that we need to take into account, that our estimates of future climate are not perfect, but we can have a semblance of realism that goes along with that. Yeah.
We can also account for changes that we're seeing in the current data in changes in the relationship between the variables as they start to evolve into this new normal that we're seeing now.
Yeah, to that point with Robin's copulas, the gammas can do that. That's it's dynamic, and I can take GScan time series for near term 5 years or whatever, and I can, use that as well. So gammas can be really flexible that way too.
I'll just say thank you again, all of you, for taking the time to present today. I think it was really beneficial. I think everyone's looking forward to hearing more about where you all go in the next couple of years.